first example, you're actually not using de Moivre's theorem because they've asked you to use a particular value for z, which is not a cis form. So we're going to be looking at using z equals a plus bi, and we're trying to factorise the expression that you've been given here. So the first thing we're going to do is solve z squared equals 5 plus 12i, where z equals a plus bi. So what we can do here is we can actually substitute, first of all. So we're going to sub z equals a plus bi into the equation. And we'll see what we end up with. So let's chuck it in. We've got z equals a plus bi, so a plus bi squared equals 5 plus 12i. Expand this out, you're going to have a squared plus, and if you can't visualise it, you know, you can put the other line. Actually, I might do it here anyway. Put the other line in for you. A plus bi squared is two brackets that are the same next to each other. So if you're not good at expanding things in your head, it's good to write them down, then you can see ABI, that's ABI. You can actually see what's going on. And then you've got that side there. Put some arrows in. So here I can see gathering together the things that are the same. We've got a squared plus 2abi, that's those, and plus, now this is an I squared here, which is a negative 1. So remember, that key important thing is that I squared equals negative 1. So I know from there now that I can simply write this as negative b squared. And what I'm going to do here is put the real parts and the imaginary parts together. You see there the real parts, there's no I. This is the imaginary part. This is the real part. That's equal to 5 plus 12i. And looking at this as well, you've got a real part and an imaginary part. So we can actually equate the real and the imaginary parts together to try and solve for a and b. Remember that the solution for this question here is given in the form z equals a plus bi. So if we know what a and b is, then we actually know what the solution is. So let's do that. We've got our real parts. The real parts equated. We've got a squared minus b squared equals 5. Okay, and the imaginary parts, and you could write this if you wanted to, you could re-express it, but I'll just leave that there. The imaginary parts, we've got 2ab equals 12, which implies that, and I'm just going to divide here by b. Okay, so we'll assume we're in that way assuming that b is non-zero. If it doesn't work, we know that b is 0. So we've got a equals 6 over b. So we've got two expressions. I'll just put a box around them. And a squared minus b squared equals 5. I'm going to call this 1. I'm going to call this 2. So I can now refer to them in shorthand. So sub 2 into 1. So we're putting this equation into this equation. We've got 6 squared over b squared minus b squared equals 5. Multiply everything here by b squared. Okay, so we've got 36 minus b to the power of 4 equals 5b squared, like that. Okay, now this is actually a hidden quadratic, so I'm just going to rewrite this, take this over to this, all this stuff over to this side, make the power of 4 positive. So we've just got that. Okay, now if we think about this, if you imagine that b to the power of 4, or b squared I should say, is like x, then you've really got an x here and you've got an x squared here. Okay, so we can do that. Let b squared equal x. Doesn't matter what you let it equal. So we'd have, this would be x squared because b to the power of 4 equals x squared, just squaring both sides. This would be 5x, and that would be minus 36. So we would have that. So now what we have to do is solve that, and we'll be able to find what b is. So I'm just going to get rid of, so I've got a bit more room. Cool. Just copy that and bring that over to my next page. So this is a bit of a long question just because the working, do that again, the working is quite long. Okay, so we can solve this. 36, 9 and 4 will actually work here. So this is going to be x plus 9 and x minus 4 equals 0, which implies that x equals negative 9 and x equals 4. Now, thinking about what x is, remember that x was b squared. So that is b squared equals negative 9 and b squared equals 4. Okay, so they're the solutions that we've got there. So if we think about that now, we'll try and solve this. So we've got here b squared. The one that's going to make sense here is 4. Now the reason for that is if we go back, can you see here that it has a bit of information about a and b? A and b are real numbers, okay? And if we look at the situation we have here, this will only give us imaginary solutions. So this one is the one that's going to give us real solutions. So it tells us that b has to be plus 2 or minus 2. Okay, let's have a look at what happens when we have plus 2 and minus 2. Now we have this relationship between a and b. A equals 6 over b. A equals 6 over b. So therefore, when b equals 2, we have a equals 6 over 2, which is 3. And when b equals negative 2, we have a equals 6 over negative 2, which is negative 3. So we have two situations here. Our solutions are of the form z equals a plus bi. So we have our solutions, therefore, solutions are z1. We've got two solutions. Z1, let's use the first two results here. So a equals 3 and b equals 2. The nice thing about this is, remember that what we started with here is a quadratic, so we know it's only going to have 2 roots. We'll go back the other root. We've got z2 equals, this time a is going to be negative 3 and b is negative 2. Okay, so they're the two expressions that we have, the two solutions that we have for our equation. So what we can do once we've got those solutions, always go back and read the question. It says solve that equation using z equals a plus bi. Well, we did that. We made our substitution for a plus bi. We substituted in, we equated the real and imaginary parts, we found what a and b had to be, and then it says hence factorise z squared minus 5 minus 12i. Now that's simply this equation here, just with everything written on the left side. So once we know the solutions, we know the factors as well. So if we wanted to factorise that expression, which is z to the power of 5 minus 12i, or z to the power of 2, excuse me, minus 5, oh, I've forgotten now, minus 12i. Then we have those factors are, remember the factors are always the opposite sign here, so it's imagining you've picked that up and you've put all of this stuff onto this side. So we've got z minus 3 minus 2i and z plus 3 plus 2i. They're the two factors that you would have for this quadratic. And you can always put those into your calculator as well to check them. So we can do that. I'll do that with the CAS. So 3 and 2i. Okay, so let's do that. So if we have 3 plus 2i, remember get the I out of that, and we've got z plus 3 plus 2i, and if we get our other one as well, we've got z minus 3 minus 2i, z minus 3 minus 2i, get down the pi menu, press enter. You can see we've got z squared minus 5 minus 12i, and let's check that. Z squared minus 5 minus 12i, perfect. So that means that this equation here has the following factors. And remember, you can check that with your CAS too. You could always take this particular equation, menu, algebra, complex, and factor. Take the equation that you have, the polynomial, and solve or factor that for z. Okay, and you can see you've got the two factors that we had, so minus 3 minus 2i and plus 3 plus 2i. So it works out that way too. So using a different method this time for factorisation, not de Moivre's theorem, but using the substitution a plus bi. It's different to de Moivre's theorem where we use the substitution z equals r cis theta. We're not doing that in this case, and if you're not using de Moivre's theorem, then you have to equate real and imaginary parts and solve the quadratic that you get from that.